My name is Fred Long. I'm chair of the BCS Mid-Wales Branch. Before I introduce this evening's speaker, a couple of announcements. For future events, please keep an eye on our website. And also, new members of the BCS can obtain a 20% discount if they join before August of this year. And the code for getting that discount will be on the slide in just a minute. I've got out of sequence with my slides. There we are. There's the code. If you want to, if you're a new member, you want to join, you can get a 20% discount by using that code. During the talk, please keep your camera and microphone turned off so that we don't have any distractions. You can put questions in the chat and we will then get to those questions after the talk. At the end of the talk, we'll have a question and answer session, and then you can unmute your microphone and address the meeting. So this evening's talk is being given by Dr. Amanda Clare. Amanda is a senior lecturer in computer science at Aberystwyth University and is currently holding a Royal Academy of Engineering Industrial Fellowship. Her research is in data analysis and data science, and in particular, bioinformatics and natural language processing and text analysis. Amanda is also interested in the analysis of sequences in general, including time series. And she is interested in formalizing components and variation from nucleotides to genes, genomes, and metagenomes. Amanda investigates interesting patterns in data using machine learning, statistics, visualization, and algorithms. Amanda is a member of the BCS and a fellow of the Higher Education Academy. So over to you, Amanda.
Hello, thanks for the welcome, Fred. And it's nice to be here and giving a talk, even if it's virtually and online and everything. Shall I share my screen?
Yes, please.
Okay, so hopefully you can now see my title slide, Intervals and Sequences, the long and the short of it.
That looks fine, yes.
Yeah. And I'd just like to thank the Royal Academy of Engineering for giving me an industrial fellowship for about 6 months. So I get to play with lots of interesting problems. And this is a talk that's not necessarily, I mean, I've started work on the industrial fellowship last month. And so it's fairly new, but everything I've been reading about the work I'm doing now has some bearing on the work I've been doing previously. And this is a talk gathered by thoughts on how actually everything is interrelated. And like with many computer science things, there's nothing new under the sun, is it? There's always just a different way of looking at it in a different field. So intervals and sequences. Let me start with a slide for predicting penguins. So this is kind of what you might see for many machine learning problems. You have some examples of different classes, and in this case, they are penguins, 3 types of penguins. And each penguin is described by a couple of attributes. And in this particular data set, the attributes are things like flipper length and body mass, which are shown on this plot here, which makes it quite difficult to distinguish one penguin from another. But also there is, I think, bill depth and bill height. And this combination of attributes for each penguin is what we use in machine learning, where we aim to build a model that automatically gives labels to each example given their attributes. By the way, this is quite a nice data set if you want to explain machine learning. If anybody out there is still explaining machine learning using the IRIS data set, you might want to rethink and use penguins instead, because the iris dataset was released to the world by Fisher, who was an eminent statistician, but he was also a eugenicist, and that paper that introduced the iris dataset was in, I think it was the Annals of Eugenics, anyway, some journal about eugenics. So if you prefer the non-eugenics connotations of classifying penguins, then I would get your penguin data from this URL. So in machine learning, we build a model and then we look at the accuracy of the model often. And we like to say, oh, our model is 95% accurate or 93% accurate. And what we mean there is for all the labels we gave to the penguins, we want to know what percentage of them were actually correct. And that's fine. But this kinds of data I've been working with lately include DNA sequences, time series data, and text. And all of these in the end are sequences, and they don't fit the normal machine learning perspective of each example of data having a set of attributes that neatly describes it. And even if they did have attributes that describe them, they're unlikely to be independent. So here we've got a DNA sequence, which is represented by a sequence of 4 letters, A's, G's, C's, and T's. And there are interesting parts of this DNA sequence. And you know, we want to understand our genomes. We want to understand the genomes of bacteria, the genomes of viruses, such as the virus that causes COVID. And we want to know, what do the parts represent, and what is the structure of this genome? What does it actually mean? And in the work I'm doing that's funded by the Royal Academy of Engineering, I'm working with Welsh Water, Dŵr Cymru, and we're looking at a load of time series data they have, because they have some water treatment plants and they have a lot of sensors on their water treatment plants that monitor how the water moves through various processes. And so we have time series data where we have a set of pairs, and each pair contains a timestamp, such as 2018, November the 11th at midnight, and then a value that's been recorded at that timestamp. And so we've got a sequence of pairs in that sense. And I also work with text as well. So I also do some natural language processing. And in text, we have a sequence of characters as well. And those characters are then blocked into words such as thanks, to, there. And those words are blocked into sentences, and sentences into paragraphs, and paragraphs into documents. But the sequence flows throughout. So sequences are data too, but they're slightly different from your standard machine learning type of data. And mostly this is because each new letter or value is not independent of the previous ones, but definitely dependent on the previous ones. And it's that dependency that makes the analysis of these things interesting. And it turns out that in so many examples, it's subsequences that are interesting rather than individual letters. And a subsequence of DNA might represent a potential gene, a unit of DNA that can be used to encode for a molecule that goes around and does something. Or a subsequence represents a time period where something interesting happened, or a subsequence in text represents a phrase or a sentence. So we're looking at sequences and we're looking at subsequences, and we want to find the portions of these sequences that are interesting. And sometimes we want to look at non-consecutive sets of letters and time points too, because it's important. For example, anybody that's been following the COVID statistics will note that we get peaks and troughs in the numbers of people infected over the week, not so many reports at the weekends, for example, and much more reports as the week goes on. So the value for one Tuesday is quite similar to the value for another Tuesday, rather than the value for a Monday necessarily. And this non-independence can be interesting and used for prediction. So if you think about natural language models that are all the rage at the moment, there are big companies working on natural language models that are going to be able to generate text. So there's things like GPT-2, which is a transformer-based model, made by an organization called OpenAI, which is not altogether open anymore, but was started as an open organization. And they've trained a big neural network, essentially, on how to absorb lots of text and use the patterns in the text to be able to predict future words. And they've trained it on lots of text from the internet in general, in particular from Reddit, but other internet text. And you can get examples of GPT-2 to play with online and type in some text and then ask the model to complete the remainder of the sentence. And we can do that because these words are not independent, right? They carry some meaning. So just as a test for the audience now, if anybody could complete that sentence, and then we'll see what GPT-2 came up with. See if anyone has any ideas. The BCS Mid-Wales audience thinks that April 2022 will bring. Any thoughts? Anyone want to type in the chat an extension to that sentence that makes sense? Just give a minute in case anyone showers, sunshine, a lot of rain, or very weather forecasting. I like the suggestions. They're all around weather. You obviously all learned from the same source of information here. A cure for COVID. Oh, that would be nice if we had that in April. That'd be really great. Unfortunately, no. The GPT-2 said things like, it gives you a variety of choices, an exciting future for web designers, or that it will bring out a great new generation of machine learning technologies, or it will bring down the US, so it doesn't matter if it is the best year for it. So the trouble with learning from the internet is you get random learning from the internet, and that can be quite US biased, and the biases that run through training data in natural language processing is one of the things that the field is grappling quite hard with now. And all this non-independence is great because it allows us to predict things, but it makes it harder to actually build the models, and it makes it hard to evaluate the models. And it's the evaluation that I started to be getting interested in lately. So let's see what we're doing with DNA. So I've been working together with Nick DeMonico, who's in the audience now, I think, and been working on finding potential genes in DNA. And in particular, Nick has been evaluating different gene finding tools. And so a gene you can think of as just a subsequence of the longer DNA sequence that has specific properties. So here's a piece of DNA. Actually, DNA that we're looking at is much, much longer than this, but this is just shortened for the slide. Here's a piece of DNA, and we want to find things in it that look like subsequences with particular properties. And in this case, we're finding subsequences that are long enough for some decision about long enough, and that appear with length divisible by 3, and that have a triplet that is suitable to be used as a start, so ATG, and a triplet that is useful as a stop, TAG, and length between them that is divisible by 3. So here's 2 example genes that we might find in this. But DNA being DNA, we can look for all sorts of possibilities, and it's not always clear which is the best ones to choose. So also in this, there's this one as well, which overlaps with the earlier one. So here's in blue, one that starts midway through another gene. And then we've got the dilemma of which one do we choose and how do we evaluate which one is better when both of them fit the properties and are overlapping. Do just paste any questions in the chat anytime anything's not clear. So this is a problem where we want to find potential gene subsequences. So we want to find subsequences for encoding potential genes. And the locations of the ends depends on the locations of the starts. And we know that they have to be a divisible number by a number that's divisible by 3 apart. And they might be long and they might be short. They might have all sorts of different properties. And they might be overlapping. They might be distinct. They might be nested entirely within each other. And the problem is that we want to find the best set overall of potential genes. So we're looking for intervals within the DNA sequence that fit a load of characteristics. And then this is actually turning out to be quite similar to the problems that I have looking at the Welsh Water time series data. So we might have, and this is just a sketch. I don't have permission to share all of their data, but their data looks something like this, where we have various sensors. We have a blue sensor and a red sensor that's measuring properties about the water. And the blue sensor reads that it's gone up and down over time, and the red sensor reads that occasionally it goes down over time. And what they want to know is, over time, when are things going wrong? When are things unusual? And when does that let them know that they should be doing more maintenance? And so they want to be able to have some code that automatically highlights regions of time where things are not as expected, where things are anomalous. So again, we're finding subsequences in time that meet certain properties. And in this case, the property is that they're not behaving normally. And so we have to build a model of what does normal look like, and then find the regions that are not behaving normally and be able to describe them. So this time series analysis I'm doing looks for these sort of anomalous regions, or even regions of interest as well. So they're also interested in not just anomalies, but various regions of interest. And these regions of interest, just like the genes that we're finding, have variable length. They might be overlapping, and there's various choices we have to make. They've also asked me to do some other analyses, not just finding regions, but finding similarities and differences between series. So if they've got multiple filters, we can compare the filters against each other to find out which ones are misbehaving. They also want to know about trends, and they want to use that so that they can predict how to best spend their investment money for 5 years ahead. And to do that, we want to be able to actually forecast what's going to happen in the future. So my thanks to the Royal Academy of Engineering for funding this work. But essentially what we want to find is intervals, and intervals are defined by starts and stops. So we want to find start and stop pairs that specify all of these intervals of interest, whether they're anomalies or genes or all sorts of things. And then if we can do that, we can find all anomalies in the water turbidity readings in 2018, or we can find all the genes in this genome that are good, or we could find the mean time between failures that we've got for the plant, or mean time to recovery, or all sorts of other interesting answers about the data. And if we were doing standard machine learning, we'd be able to make a load of models, and then we'd be able to measure the correctness of these models. And like with the penguins data I showed at the start, a very common thing in machine learning models is accuracy, the percentage of things we got correct out of all of the things. But nowadays, that's not quite enough to give a full picture of what's going on with our model. And it's very common to see also now precision and recall and specificity. So with accuracy, it gives you an overall figure, but it doesn't give you the detail of what's going on. So with precision and recall, we have the kind of how did we do, let me just say it in the maths that's on the slide. It's not really maths, but how many things we got right out of how many we said there were. So this is how good our answers were when we made them. And then recall is more about how many we found out of how many we should have found. So we could have better precision at the expense of worse recall. We could get more right just by not predicting very many, but only predicting the really ones we're really confident about. Or vice versa, we could get better recall by having worse precision. So we could find more, but we'd also find a load that weren't actually right. And so recall is also known as sensitivity. And then there's specificity as well. And this is the kind of thing that we often want for medical diagnosis. So how many non-events we also got right out of how many non-events or non-genes there were. So if you're doing cancer treatment, you want to know how many people you labeled that didn't have cancer that you got right, as well as how many did. And so we have these measures, and that kind of lets us break down the accuracy a bit more into precision and recall, and then balance those two things and decide whether we prefer one or the other in our model, or whether we actually prefer both to be maximized. And so we have, in order to do those things, we have these concepts of true positives and true negatives, and false positives and false negatives. So we can have true positives were things that we predicted to be correct and actually were correct. So they're in the bottom right-hand corner of this confusion matrix, as it's called here. They're the number 38, where we predicted it to be correct and it actually was correct. Whereas the true negatives are the ones where we predicted them to be no and they actually were no. And so with a confusion matrix, you want most of the values to be on the diagonal of the matrix. And then the ones that are off the diagonal, you want them to be lower. They're your false positives and false negatives, where you've falsely made that prediction. And that's all great. So this is standard machine learning. We can provide confusion matrices, and we can provide precision and recall and true positives and true negatives and so on. But then what does all that mean when we have a setup where actually what we want to find is subsequences or intervals? And it gets tricky because they don't give you the whole story. So here's 3 examples of where we might make predictions and they might agree or disagree with reality. So on the top bar, I've got reality, and there's 3 blue genes or 3 blue time intervals. And on the bottom bar, we've made some predictions. In the first case, we've made the prediction exactly right. It exactly aligns with the reality. In the second case, we're off by a bit. We started early and we ended early. So not quite exactly right, but it still feels pretty good. And then in the third case, we missed it entirely and we didn't make a prediction where reality had something. And really, we could do with better measures of accuracy that are interval-based and range-based and capture all of that stuff and are not just point-based. And then we get sort of really awkward situations like this one, where we've made a prediction, but is it close enough to reality even to count it as the same thing? Or is it just a coincidence that this is overlapping by a bit? And in the second case, our reality is spanned by 2 different predictions. And do we count either one of them or both of them? And is it okay that there's a gap in the middle and it wasn't a continuous event or continuous gene? And really, our measures ought to be accounting for all of these issues and showing us what's going on in the same way that precision and recall show us more about what's going on in a standard machine learning environment. And we can apply some of the other metrics. I mean, in the standard machine learning world, there's all sorts of metrics actually, and we can apply some of these. For example, we could apply a very trendy one in bioinformatics at the moment is the Jacquard index, which is the ratio of the intersection of 2 sets divided by the union of 2 sets. So we're looking at, for any 2 sets, what they share, what they both have, divided by what they have between them as a measure of how similar they are. And so if we applied this kind of concept to our interval prediction, we could say that when we predict exactly the same positions as reality, then the intersection of the predictions and reality is the same, and the union is the same, and then the Jacquard index is just 1 because we have 1 divided by 1. Oh, if anyone's unsure, these vertical bars are representing the size of a set. So the size of R intersect P and the size of R union P. Yeah, and then if we move to the middle case, here we're predicting slightly different positions than reality. So the union of the positions is larger than the intersection now. So this Jacquard index will be some smaller number divided by some larger number. So the Jacquard index is less than 1. And then if we move to the final case, here we're predicting nothing like reality, and the intersection is 0. So the Jacquard is 0. So these kind of measures can give us numbers that allow us to say something about what's going on. But then what actually happened for us in the gene prediction and counting whether gene predictions were good or not is that Nick, who's in the audience, this is part of his PhD work, and he's now published this paper of a tool that lets us compare lots of gene prediction tools on many measures. So we had a load of debates about what should we be measuring here, and I'm sure you can ask Nick more about it later, but we ended up including 72 measures for measuring how well the gene finding tools work. And these include all sorts of things like whether the starts were perfect, whether the stops were perfect, whether both starts and stops were perfect, the difference from the start and stop positions, the median difference, and the true positive, the false positive, the true negative, the false negative for the genes as a whole and for individual letters. So we're capturing were the whole units found and were they found more precisely because the individual letters make a difference, whether they've hung off the end, as it were, or too short. We've got measures that look at the length differences we found, and we've got measures that express the idea that a prediction that covers 75% of the reality of the gene and is in frame, this is a bioinformatics term, and has the right properties, is one that we call a better prediction than most. We say that's detected rather than just predicted. And so we can have this sort of, we can count the number of things we found, and we can count the number of things we found that overlap by 75%, and that's much better. And again, 75% we could change as a number depending on what people want out of their data. So we could add a whole load more. We don't need to stop at those 72, but we did for this paper. We could add all sorts of interesting coefficients and measures. There's the Forbes coefficient, the ratio of observed to expected number of events found in both the prediction and the reality, or in the outputs from 2 different gene finding tools. There's the Matthews correlation coefficient, which summarizes a confusion matrix down into one figure. There's F1, also Sorensen dice if you're looking at binary classification, but F1 if you're looking at more, which balances recall and precision. We could add the number of overlapping intervals, the distance between the nearest intervals, the interval midpoint differences, robustness to noise, some measures of ambiguity. We could add a whole load more, and I feel like we should be adding a whole load more. And people are beginning to take this and run with it for other fields as well. So we're getting things like this paper in 2018 in the NeurIPS conference, which is one of the biggest conferences for machine learning there is now. And well, it is the biggest machine learning conference. So precision and recall for time series. So people starting looking at what does it mean to have precision and recall for these sort of interval-based predictions. And they've decided that precision is the fraction of all detected anomalies that are real anomalies, and recall is the fraction of all real anomalies that are successfully detected. And they will define them to be composite, made up of useful information. So their recall is the weighted sum of existence. So did we spot any part of it? And we'll give that a weighting. And overlap, which is like how many predictions are there for this interval and the size of the overlap of the interval. And maybe we'll pay more attention to whether it overlapped at the beginning or the end, or the middle. So you can have weightings for all of these things. And then precision, which looks at how many intervals there were for this prediction. So sometimes you can predict, you can make a prediction that covers multiple real intervals. And again, so we can have a weighting that balances recall and precision, and recall itself is made up of parts and precision is made up of parts. And I feel like in these papers where they do that kind of thing, they've understood the complexity of the problem, and they've gone away and given a way of calculating the parts, but then they've still tried to summarize it all into one weighted number. And I think that's then losing the benefit of collecting the parts. This next work was in CIKM 2019, Time Series Aware Precision and Recall for Anomaly Detection. And they looked at how many anomalies are detected and how precisely each anomaly is detected. So they broke it into, can we find it? And what portion of it did we find? And that's very much the same as what we have in Nick's work, where we're looking at a measure of detection that says we must have at least 75% detected. And again, they have weighted sums of these parts. And then from software engineering, we have inspiration. So this is a paper in 2020 in ACL, which is the Association of Computational Linguistics. So this is in the natural language processing text analysis field, where they are suggesting that they are inspired by software engineering black box testing and what's known as metamorphic testing, which is an advancement on property-based testing. So in software engineering, we can write properties, we can write our functions, and then we want to test whether our code works well. And we write properties that say something about what our code should behave like. And then we can generate lots of inputs and test that they satisfy the properties. And metamorphic testing takes that to a higher level again. It allows you to write properties about your system, even when you don't know what the right answers to the data inputs should be. So if you were looking at testing a system you've built that books flights, for example, and you ask your system to book a flight for 3 people to New York, then the system will give you an answer back and it'll be a list of flights. And you don't know whether those flights are correct or not unless you've gone and really looked at all the data and all the possibilities and built your test harness. But what you do know is you got some answer back. So then if you asked the system to book you flights to New York for 3 people leaving on a Wednesday, you would expect the number of flights to New York to be less than you got previously, or the same or less, but certainly not more when you left the question more flexible. And so it's kind of a feel for what metamorphic testing is, that you can devise tests even not knowing what the answers are, because you can devise a test and then devise another kind of test that knows something about the structure of the data rather than specifics of the data. And they want to use that in natural language processing. They want to be able to provide a framework that lets people who've devised natural language processing systems make examples that show the model should have certain behavior. So they want to allow people to do, to be able to say that this model should predict the same thing if we give different input perturbations. If we change the input in this way, we know the model should give the same answer. And if we change the input in this way, we should know that the model gave the opposite answer. Say we're predicting sentiment, positive or negative feeling of a piece of text. Then if we added certain really bad review sentences, like I hated this restaurant, to the end of an existing review, then you would know that that wouldn't make the sentiment more positive, even if you didn't know what sentiment the model was going to give you back. And so I think people are beginning to look more at testing of these AI systems and add more expressiveness to the testing systems. We are no longer just interested in precision and recall and sensitivity and true positives. And we're certainly no longer just interested in a single accuracy figure, because we want to understand more about what's going on with our systems. And so, yeah, what it's shown me working with sequences over the last few years, what it's shown me is that so much of machine learning and data science and AI when I look at that for how do we evaluate this, so much of the sort of typical learning is evaluated to a single figure, or maybe 2 or 3 figures. But actually, there's a whole load of different measures that are important to different scenarios. And each of these measures explains something about the system. And so if we have 72 measures or 140 measures, then we can compare different systems with each other, and we can see in what way is this one better or worse than this one? In what way do they share properties or don't share properties or do something that's different? So having this sort of collection of figures will help us explain different aspects of the model, what it's good at and what it's bad at. And this is linked into the whole push now for more interpretable machine learning. We want inspectable algorithms. We want to understand what the machine learning is doing and who will it be bad for and who will it be good for, and in what cases should we be considering to improve the system. And we should then be doing bigger, better evaluation that allows this inspection. And, you know, we've got this sort of phrase of deep learning, which is all the rage at the moment. We have deep learning, which just essentially means neural networks with many, many layers and many, many connections. But I think what we need to become as a field is more comfortable with deeper evaluation. It should be more routine, not just to produce a couple of accuracy measures, but to produce a much deeper evaluation of your system. Anyway, I'm going to finish with a slide that says, if anyone out there is evaluating sequences or regions or intervals or time series, then come and ask us. We've got more measures than you know what to do with. You won't even be able to shake a stick at them. But all of these measures will help you understand the systems and will help you claim victory in various areas. And my email address is at the bottom of the slide, and I'm going to stop there and take questions. If anyone wants to ask any questions
Thank you very much.
The chat, I presume, but I'll hand it over to Fred for managing that.
Okay, yes, do either put questions in the chat, or you can now unmute yourself.
In the meantime, I'm going to just paste in Nick's paper in case anybody fancies reading and checking out the 72 measures.
I can see a hand up there from Mario. Hi, Mario. Do you want to unmute yourself?
Yes, I was not allowed to unmute myself. Now I can. Thank you.
All right.
First, I want to thank you and congratulate you about this presentation. Excellent talk, really very enlightening, and you explained very well the topic. I have very fast question. What do you suggest when we have sequences with different length? What measure do you suggest to compare them and this kind of stuff?
When you have sequences that have different, what? Sorry, I missed something. Length. Oh yeah, that's really annoying, and I do have some of those. So if you have time points that line up, or in some sense a structure that lines up, we can do subsetting of the sequences. But if they don't line up at all, then we have to kind of do some shifting. So if you've got time series, you might want to look at dynamic time warping.
Yes, I know about that.
Yeah. So that will allow us to basically match points from one sequence with points in another sequence and then compare those.
Very good.
I'm finding that it's troubling to me I don't really want to interpolate my sequences because they my time sequences in particular, because they bounce around too much for me to interpolate between them. So
okay, so you don't suggest interpolation because that was an option also.
That depends on your sequences. If your sequences are smooth enough, then I would.
Okay.
But mine tend to be quite sharp and spiky. So
Nice. Excellent. Thank you so much. Thanks again. And really very enlightening talk. Thank you so much.
Okay, so it looks like we might need to ask people to unmute if they want to speak. So if they just put their hand up with the Zoom prompt, or just type into the chat.
No more questions. You've floored everybody, Amanda.
I was thinking when so this isn't a question, it's just more a comment. So when I was recently out of university, we did some work with a steel producer who had an enormous machine which rolls steel. And they really wanted to know similar things. When do they need to do maintenance? When is it about to go very bad? And because very bad for them could take their machine out of action for several days as they pick the bits of hot steel out of it. And we were trying to use what was it, expert systems in those days, and it was pretty darn hard. This looks promising.
So that's the classic AI thing, isn't it? Whether you have expert systems and you manage to encode rules that represent human knowledge, or whether you do it the stats-based approach, kind of gathering enough past data and learning from it. And I think in practice, a lot of models might start as a statistical model and then end up being augmented by rules nowadays, don't they? As it gets embedded within industry.
Yeah.
I imagine there's a lot of rule-based systems actually still in production.
I could imagine. Yeah, we made some progress, but in the end, it wasn't strong enough to justify continuing the project. So
if any, see Hannah's question, not question, comment, but if anybody has any cool measures that they would like to be collected and put somewhere, then please do send them and we'll collect them together and list them. Yeah, so Welsh Water,
Amanda.
there's a question from James Cooper. Can you tell us any more about the Welsh Water use case? So yeah, they've basically got water treatment plants, which are essentially filtering the water through various filtration processes and removing stuff in the water and then sending it out clean. And depending on the water site, they do different treatments, but mostly filtering and maybe UV sterilization and adding chlorine. And so they've got various monitors throughout the systems that check on the water quality coming and going from each stage. And so what they want to know, like the filter beds are big sand beds, and they're expensive to dig out all the sand for maintenance. So one of the things they want to know is, when are the filters not behaving as they should? But they've got other questions as well about raw water quality and whether the E. coli counts in it can tell us something about the way the water's behaving. So they've got all sorts of different data. And honestly, since I started this fellowship, they keep throwing more, and can you also ascertain this for us? And can you also ascertain that for us? Whether it be but it boils down in computer science terms to mostly find the anomalous regions or find the trends going on here. In order that they can best spend their money on sorting it out in advance rather than waiting too late.
So your project with them is for the full 6 months, is it, Amanda?
Yeah, so it's and I recommend the scheme that the Royal Academy of Engineering, they fund for either 1 year or 2 years, part-time or full-time. So I went for 1 year part-time. So although the funding is for the year, I'm working full-time for 6 months rather than full-time for a year.
Okay.
So that I could do my teaching term in semester 1 and then research from semester 2 in the summer.
Mm-hmm.
Oh, it's the first time I've had a pop-up that says Chuan's raised a hand.
Oh,
But I don't.
all right. Sorry, I will.
I don't know how to deal with it.
It's all right. I will. Can you speak now, Chuan?
Yeah, thank you, Amanda. Very inspiring. Yeah, I was thinking about some of the computer vision areas. They have also like object detection. So there are similar kind of concept, like detecting the the session union, area union, something like that.
Oh yeah, that's a good thought. I hadn't looked at computer vision.
Yeah, and have this kind of average precision. So basically, you set a threshold like 75%. They have this average kind of precisions. You can change the threshold and like summarize the precision together as a kind of measurements.
Oh, I shall have to steal some measures from computer vision now as well.
Yeah, I feel that's kind of sequence. Yeah.
I mean, they essentially have two-dimensional or worse.
Yeah.
Rather than intervals which are one-dimensional.
Yeah, we can just focus on one dimension, and you can also get the kind of combining the unions, the areas, intersection areas with the positions, so they have the regression in terms of position.
Yeah.
Plus the classification. In that kind of areas. So that would be interesting.
Nice.
Yeah.
Nice, and I can see Hannah's gone for 2 and 3 and 4 dimensional, depending on where the time is there. So yeah, you're thinking of your 3D modeling and then in time as well as space, presumably. Yeah,
just the comments.
Yeah, I'm gonna have to find more measures now. It tells me there's some other raised hands.
Yeah, so
yes.
Mario again?
Yes, I have another question, please. What comes to your mind, like when you want to compare your work with another time series classification algorithm besides the neural network long short-term memory? Other than that, what do you think of, like which algorithm, which neural network,
so for neural networks, if we wanted to use neural networks for finding genes, do you mean, or for finding anomalies in time series?
Yes, for example, or other time series. But yes, this is a good example. Yes.
Yeah. I mean, I'm particularly inspired by what they're doing in the natural language processing field, where transformer networks are the thing, and the idea that they can take into account quite long-range dependencies. So in your sentences, basically the words that are going to come next depend on not just the previous word or the previous 2 words, but words way back in the sentence. And so there's this idea of attention. So there's weightings applied to focus attention on different parts of the sequence. And I think that's got to be true for time series. And it's also got to be true for DNA as well.
And other than that, do you have any other suggestion other than transformers and this kind of network?
No, to be honest, neural nets is not my field. So I would go
other than neural networks, for example, like in the classical AI or something that deals with time series and this kind of stuff.
Yeah, my time series that I have so far from Welsh Water are either incredibly long or incredibly short, and none of the methods are ideal for those kinds of examples. Short time series, you can get away with basic regression, but very long time series, that long distance, what happened 3 years ago, 4 years ago, when the weather was more similar to what's happening currently, but you have measurements every 15 minutes, is quite hard to absorb in a model. Okay, very good. Thank you. I don't have a good answer to that question yet. No, that's but I only started in February. Cool. No, thank you very much.
Yeah, Chuan has a hand up.
It might be legacy hand.
it might be a legacy hand, but I've said you can unmute if you like, Chuan. I'm not quite sure why they've put this security restriction on us.
Sorry, this is a legacy hand. I can't. Yeah.
Okay.
I don't know how to remove that hand.
Okay. I think I can.
I've removed it.
Let's go. So one thing that'd be good to see is two Zoom and Teams managers just to get rid of the hands after a short while once the person starts speaking.
Features they haven't yet implemented.
No, it'll still be 12 years before it gets to Linux.
Hmm.
Are there any more questions? I'm sorry I disappeared for a short while. I lost my internet connection.
All right, we had a nice power cut here halfway through, but thankfully my battery kept going. Actually, which means the internet kept going. That's impressive. Everything else went. Curious.
Mm.
Well, thanks very much, everyone.
Yes.
Oh, thank you, Amanda. That's really interesting.
No more questions. So yes, thank you very much, Amanda. That was a very interesting talk. It sparked some interesting questions. And so thank you very much.